Hello everybody, I'm Amirmasoud Molaei. I'm so sorry that I was not able to participate in person in the conference. Today I prepared a brief presentation about my paper. The topic of my paper is evaluation of deterministic models for the excavator theoretical productivity estimation in the digging and trenching operation. I want to say thank you to other authors, Marcus Geimer from Karlsruhe Institute of Technology and Antti from Novatron company in Finland. Let me introduce myself. I'm Amirmasoud Molaei. Uh, Currently, I'm a PhD student in Institute of Mobile Machines, MOBIMA at Karlsruhe Institute of Technology in Germany. It is less than 2 years that I'm working in Novatron company in Finland. In the MORE project, there are 8 PhD students that are working on the robotization, automation, and digitalization of the heavy-duty mobile machineries. Heavy-duty mobile machines are so important and plays a main role in different industries such as mining, forestry, and construction industries. They have a different challenges such as shortage of skilled human operator, harsh environment, lack of safety, low productivity. The productivity construction sector has been increased only 1% during the last 20 years. The studies show. And also another challenge is the equipment cost. 5 to 10% of direct costs in building project and up to 40% costs in highway construction project are related to the heavy duty machines. If you cannot measure it, you cannot improve it. Probably you heard this sentence. If we want to improve something, firstly we need to measure the productivity. The traditional method for the productive monitoring are based on the human um, and manual observation. They are time consuming, costly, and error prone. We need an automatic method for productivity monitoring. It can help us to reduce the operation time, fuel consumption, and cost. It can also help us to optimize planning and working parameters to efficiently managing ongoing projects as well as accurately costing and budgeting the future projects. Also, it can help us to identify the potential project issues and improve the management economic situations. Our application in this paper is the hydraulic excavator. This machine consists of three main parts: traveling body, space body, and truck digging manipulator. And two important tasks for the excavator is the digging and trenching operation. Firstly, we should define the productivity. In the productivity of excavator in digging and trenching operation, there are two important parameters: the quantity of the material and the operation cycle time. The operation cycle time consists of the time for filling the bucket, swinging loaded, dumping material, and swinging empty. Uh, the product definition for the digging is the amount of the material, the volume of the material per time, and for the trenching operation is the length of the trench per time. There are different conditions that can significantly affect the productivity of excavator in the digging and trenching operation: size of excavator, bucket capacity, repair and maintenance, or condition of the machine, digging depth, and swing angle of the operation. Relative height, actually the height between the digging and dumping position. The dumping condition may be sometimes it is a small truck or sometimes it is a big pile of material. Also the type of the material. When the material gets hot, it takes more time to do the operation. Site congestion, skill of the human operator, and also the weather condition can affect the uh, productivity of the machine. We need to specify the production performance ratio of the machine. Actually, the closer the index of the production performance ratio is, to find the high the machine performance. In this index can help worksite manager to compare the machine productivity with the capability of the machine, so ensure the machine works at full capacity. meet the needs of the project and provide a high return on investment. We can calculate this index by using the actual productivity and theoretical productivity of the machine. In this paper, we focus on the theoretical productivity of the machine. Uh, there are some ideas how to calculate the theoretical productivity. For example, from the construction equipment management handbooks, we have a method from the we have a model from the Caterpillar and Common. So, but the model from Caterpillar cannot be used automatically because it needs a descriptive model and it's the human. But we focus on the PML model from German and also the Komatsu model, and we develop them for the using the automatic manner. Uh, Firstly, we need to define the PML model. Uh, Here you can see the formula for the PML model. We have the heap bucket capacity. There are two different standards for the heap city, and the SAE standard, Society of Automatic Engineers, and also the CEC standard committee for the European construction equipment. In the figure, you can see the difference between two standards. The SAE standard is bigger than the CCS under around 10 to 20%. Another parameter is a bucket fill factor that we should specify based on the type of the material. Another parameter is the theoretical cycle time. Also, we have two modifying parameters: swing angle factor and digging depth factor. Here you can see the formula for the bucket fill factor, theoretical cycle time, swing angle, and inlet factor. Firstly, we have a table. We have four different type of the material: high, medium, low, and very low excavated type of the material. And we have a fill factor for each group of the material. Another step is the theoretical cycle time. We have a two formula. The first one is for the high and medium, and the second one for the low and very low type of the matter excavated material. Also, we have a formula that calculated swing angle factor based on the swing angle of the operation. And also we have a two formula for the digging depth factor. The first one is for the high and medium, and the second one is for the low and very low X type of the material. Now we have the Komatsu model. In the Komatsu model, we use the heap bucket capacity based on the SAE standard. And for the bucket fill factor, we have we have a table that you can see for different type of the material. We have a different fill factor. When the material gets harder or bigger, the fill factor make it smaller. And also we have a theoretical cycle. We should calculate theoretical cycle and also the conversion factor. Here in this table, you can calculate the theoretical cycle time based on the swing angle of the operation and also the capability or the model of the machine or the size of the machine. When the machine is bigger, this it takes more time to do the operation. Theoretical cycle time is bigger. But here you can see the calculation of the conversion factor. Conversion factor is calculated based on this table. Actually, in this table there are two parameters: digging depth condition and dumping condition. There are three groups for the digging depth condition: below 40%, between the 40 to 75%, and over 75%. And for the dumping condition, we have a four different groups: the easy, normal, rather difficult, and difficult. For the easy, it it defines dump onto the small pile. For the normal, it is a large dump target. For the difficult, it is a small dump target. And for the difficult, a small dump target requiring maximum dumping reach. And it is the definition of the conversion factor in this formula. Now we are extended the theoretical productivity for the tranching operation. We the definition of the product in the tranching operation is the length of the tranche per time. We get some help from the product definition for the digging operation. Actually, as you can see, we are using the definition of the product for the digging operation, and after that, by using some modification, we try to calculate for the trenching operation by using two new parameters, and the swell factor and also the cross-sectional area of the trench. In the first part, we need to change the definition of the volume of the material. In the digging operation, uh, all definition is based on the loose volume. The loose volume is the volume of the material that is piled in the stockpile or the back of the dump truck in a loose condition. But in the trenching operation, we should switch to the bank condition, bank or unexcavated volume, the amount of the soil that is already in the ground. By using the swell factor, as you can see in the table for different type of material, we are changing this definition, this volume definition from the loose condition to bank condition. But for the from for the change from the volume to the length of the trench, we need to know the cross-sectional area of the trench. That this cross-sectional area comes from the building information modeling. By using the designed model, we already know how much is the cross-sectional area of the trench. By using the common and BML model and also the cross-sectional trench and also the swell factor, we extended the definition for the trenching operation. One important point that should be considered before analyzing the result section is that for the automatic calculation of total productivity in the digging and trenching operation, we need to know some inputs. What are they? Are the swing angle of the operation, digging depth, type of the material. Uh, in one paper, we mm, in one of the references of the paper, we we presented a paper that automatically we can calculate the swing angle of the operation, also digging depth of the operation. I mentioned this point to clarify everything about the and also the type of the material samples. It's suppose they are now. Firstly, we try to analyze the swing angle and the effect of digging depth on the this formula, this definition. Firstly, we perform the swing angle analysis. We suppose the pile of material is on the ground surface, the depth is around zero. The swing angle change from the 45 to 180 degrees. The absolute difference is, as you can see in the figure, the absolute difference between the BML and Komatsu model is less than 3.5 seconds, and the Komatsu model, it seems it is more sensitive to the swing angle variation. And the theoretical cycle time in the Komatsu and BML model increased approximately 55 and 19% respectively, based on the swing angle variation. And but for the digging depth analysis, we say for the swing angle of the operation is around 90 degrees. The absolute difference is less than 2.5 seconds in two models, and the car cycle time in the command implement model increased approximately 22%. In two models, it is approximately the same. And it is obvious that car cycle time obtained from the BML model are approximately 15% greater than the Komatsu model. The Komatsu model is more optimistic and the BML model is more realistic and conservative. Here we did some real measurements, some real operation to be able to analyze what is happening in the real world. That we use a Komatsu uh, excavator brand Komatsu PC, and the heat capacity of the our excavator based on the SAE standard is 0.35 cubic meters. The dumping maximum digging depth capability of the machine is around 5.48 meters. The material in the operation, sand and gravel, the dumping condition is a long-term target. We did 4 experiments. 2 experiments have been performed by experienced operator and 2 experiments by inexperienced operator. And also we perform the methods for the automatic swing angle depth estimation. Here you can see the result of the swing angle estimation. In 2 experiments, we the swing angle is around 120, and in 2 other experiments is around 60 degrees. But the result of the digging depth estimation has not been shown because the pile of material is on the ground and the digging depth is zero. Zero, zero. Here you can see the experiment. In the first and second operation, they have been done by experienced operator, and the swing angle is around 60 and 120 degrees. Um, and also the third and fourth operation, and they have been done by inexperienced operator. That swing angle is approximately 60 to 120 degrees. As you can see, the real cycle time by inexperienced operator is more than the experienced operator, and also the theoretical estimation, theoretical product estimated by the Komatsu model is lower than the BML model. And in the as you can see in the figure number 10, you can see in 1 or 2 cycles, the experienced operator is working even a little better than the theoretical product, better than the expectation. In this paper, 2 automatic methods for the theoretical productivity estimation have been proposed. Theoretical productivity estimation for the excavator in the digging and trenching operation. One of them is called PML model, and it's called Komatsu model. Also, we extended the method for using for the trenching operation. Firstly, the effect of swing angle and digging depth on the Komatsu and PML model have been analyzed. It has been studied that behavioral model is more conservative and favor a more realistic theoretical cycle than compared to Komatsu model. But the Komatsu model is more optimistic and indicates statistical sensitivity to the particular elements such as the swing angle. Also, in the future, we need to model a falling factor in the trenching operation because the operator spends some time for the killing the trench. This parameter should be considered. Also, in this operation, the dumping condition type of the material has been supposed they are now, but in the future we need automatic method for the material identification, also dumping condition identification. Thank you so much. Uh, if you have any question, I happy answer, and here you can see my email. Thank you so much. Have a nice day.